Yes, combinatorics is the fancy word for accounting. So here's our fundamental counting principles. How many different cars can be built? How many decisions would you have to make? 3 decisions. You'd have to make a decision for color, transmission, and your interior. How many choices do you have? 3, 2, and 2 gives you 12 ways. So that fundamental counting principle probably works the best here. You could also do a tree diagram. Quickly write down your answers for example 2. And how did you do? Did you get 3 spaces, 3 spaces? Without repetition would be 7, 6, 5. With repetition would be 7, 7, 7. And you could figure those out. This is 210. And this is, what is that, 343? Is that right? And now we're going to add something new. We're going to add a restriction. So this is our first time in these notes that we run into something new. The strategy when you have a restriction with the fundamental counting principle is you deal with that restriction first. So how many 3-digit numbers? Again, I'd like you to only use the numbers. We're still going to stick with 1 to 7 here. How many 3-digit numbers are even without repetition? So if it's an even number, there's a restriction, and the restriction is on this last space, that it has to be even. How many choices do we have for that number? 3. It's either 2, 4, or 6. So you put a 3 in there. How many choices do you have for the first number? No. 6. Because you've already used up one of your even numbers. So you have to deal with the restriction first, and then you can go 6, and then there'll be 5 for the middle one. If you had tried, you still called this one even. This is the reason why you have to deal with the restriction first. If you didn't deal with the restriction first, you would have told me there's 7 choices here. And then you would have told me there's 6 choices here. And then I'd say, well, how many choices are for the last one? And you might have said, well, because it can be 2, 4, 6, I think you should be able to put 3 there. But then I said, well, what happens if I picked a 2 to begin with? Then I wouldn't have a choice of 3 to end with. Does that make sense? So whenever you have a restriction that something has to be something, you have to deal with that first. So here's one for you to try. Again, use the numbers 1 to 7. And once you get your answer, I want to see if you can think of another way to get the same answer. I'm guessing most of you use that as your first strategy. Did someone see another strategy to figure it out?
Take the number of all the numbers no matter odd or even
Right?
minus the even ones.
So we figured out earlier that there was 120 if you weren't allowed to repeat. We figured out that there was 90 even ones. And if you take all of those and subtract the even ones, you're left with the odd ones. Okay? And this is a strategy that will come up then we're going to call this the not strategy, where you count all the ones that are not what you want and subtract them from all the possibilities. And sometimes that's an easier way of counting than trying to count something directly. How many 3-digit numbers? By the way, is 095 a 3-digit number? No, because that's a 2-digit number. That's 95. So we're not looking for 3-digit codes, because you could have a computer code where you have to type in 095, and that would be a 3-digit code, but that's not a 3-digit number. So we're going to say a 3-digit number doesn't start with a 0. And you're not allowed to repeat. Is there a restriction on this? What's our restriction? So the first one can't be 0. So how many choices do I have for that then? 9. Okay, now, because it does say using all the numbers 0 through 9, we would have 9 choices. How many choices then, if there's no restrictions here, do I have for this one? 9 again. Because you've used up one number, but now 0 can get put back in. Now you've used up 2 numbers. There's 8 left. $648. This explanation word is okay for A and B. The explanation word for C should be simplify. So evaluate means get a single answer in the end. Simplify means get rid of the brackets, get rid of the functions, get rid of the factorial signs, and just write it as an expression. Are there any of these you'd like to go over? So for B, I would start, the biggest one is 10 factorial, so I'd start expanding the top. 10 times 9 times 8 times 7. And when I get to 6, I'd say, hey, I've got a 6 factorial on the bottom, so I'm going to cancel those out. I have a 4 factorial on the bottom too, so I'm going to expand that one. 4, 3, 2, 1. Are you okay that 4 times 2 is 8? And now, 9 divided by 3, if I simplify that, that would just be 3 on the top. 3 times 7 is 21. 21 times 10 is 210. Other ones are okay? So we always expand the biggest one. And even when we're in variables, you have to recognize, does it make sense that n plus 2 is bigger than n? So you start expanding. N plus 2 times 1 less, n plus 1 times 1 less would be n, and that n factorial would cancel out with the n factorial on the bottom. So this is, a lot of this is review. Permutation, we've already had this definition where the order matters. If you rearrange ABC, if you think about the fundamental counting principle, you know you should get 6 of them. Could you write out all 6 of them? Probably. And then we've had our formula already as well. NPN would be n factorial. By the way, remember that the definition of 0 factorial is 1. Anybody in the wind ensemble? No? Okay. So if they have 10 pieces of music and they want to make a program where the order matters, because sometimes you want to start with O Canada and sometimes you don't want to start with O Canada. It's kind of funny if the O Canada was the third song in a program, people would feel a little weird. But so the order would matter when you make a program. There's 4 decisions you have to make. How many choices do you have for that first song? 10. Then 9, then 8, then 7. This is the same as 10p4. And you could type this in your calculator and get an answer. Okay, I want you to try the next 2. Actually, the next 3, and we'll put the answers in a second. Number of permutations of the word math. Did you get 4 factorial of 4 times 3 times 2 times 1? Yeah. And that's equal to 24. If there are 12 desks, how many ways can the students be, 5 students be seated? The first thing in this one is the common mistake is you think students sit in desks, so you make 12 spaces. There's not actually 12 decisions that need to be made. How many decisions need to be made are only 5. Each student that comes in makes a decision. Student 1 comes in. How many choices do they have? 12. Then 11, then 10, then 9, then 8. This is the same as starting with 12 choices. Whoa. 12, whoa. There we go. 5 spaces, 12p5. There's 21 people in class today. There's 33 desks. And this is where the formula is nice, because to draw 21 spaces and start with 33 would take a lot of space. So if we figure this out, this is how many different random seating plans could be made. So I could spend the evening writing all the possibilities out by hand, and the next day bringing in the barrel with all the pieces of paper and picking one out at random and say that's our seating plan. Do you know how big a number this is? It's a very big number. Okay. Egg. What kind of, and let's change this because we've talked about this. Take out the word repetition here, and let's change it to identical objects, because we've done this before. So permutations with identical objects. How do we deal with identical objects? We divide out the repetition. There's 2 G's repeating. In Assissippi, 1, 2, 3, 4, 5, 6, 7, 8, 9 letters to begin with. But we have 3 S's, 2 P's, 2 I's. The hard thing about identical objects is recognizing that the word problems are identical objects. So here's a contractor who sold model homes of type A, B, and C on a street. 3 of model A, 4 of model B, and 2 of model C. How many ways can those houses be arranged on that street? Well, you'd have to say, well, these are identical. And it's like a Mississippi question. Nine factorial normally, but we have 3 A's, 4 B's, and 2 C's. Try this one on your own. So here's his house. It is north 3 blocks, 2, 3, and east 1, 2, 3, 4, 5, 6 of school. Okay? If, how many different routes can he walk home? He needs to go north 3 times. Oh, am I in the wrong place? He lives east. So the school needs to be over here, and his house needs to be over there, right? Because he lives 3 north, that's north, and 6 east. Yep, that's right.
Oh, of the school. Sorry, I was thinking.
Okay. So in order to get home, he needs to walk north 3 times and east 6 times, and wherever he decides to walk those creates a different path. This is identical objects question. And we can type that into our calculator to find it out if we wanted to. So this identical objects, we've done this already. Here is something new. We are going to call these grouping questions. Sometimes you like to arrange things in an order, but you like to keep certain things together. Maybe you have books at home. And maybe you want to keep all your mystery books together and all of your sci-fi books together and all your romance books together. I'm not sure what kind of books you have, but maybe you want to organize them by the different types. Or maybe you want to organize them by color. I want all my books that have black bindings together and all my books with red bindings together. So you've probably done some sort of organizing in your room at some time and decided to group certain things together. And this allows us to figure out how to count these things. The basic idea is we count how many groups that we want and first rearrange our groups. Once we've rearranged our groups, we look within each group and see how many ways we could rearrange things in that group. So it's probably easiest to see with an example, so let's look at the first example. Probably something that happens to you at home. You've got all your math books and you want to rearrange them on your shelf. So here I've got my 4 calculus books, my 5 algebra books, and 4 geometry books, and we're going to assume that they're all different. Okay? Wouldn't make sense to have 4 calculus books that are all the same. You want 4 different calculus books. So I have 3 groups. So first I have to decide, do I want my calculus, then algebra, then geometry, or maybe calculus, geometry, then algebra, or maybe I should put my algebra books first. So because I have 3 groups, there's 3 factorial ways I could arrange those groups. Then, once I've decided my groups, then I have to rearrange my, well, let's start with our calculus. Can you see that your calculus books could be put in 4 factorial ways? Because there's 4 of them. And your algebra books in 5 factorial ways. And your geometry books in 4 factorial ways. And it's kind of similar to a decisions question. You have 3 main decisions to do. First decision is what's the order of your groups? Then you have to say, once you've ordered your groups, you have another decision, how am I going to order my calculus books? And there's 4 factorial ways to do that, because there's 4 books. And then how many ways can I order my algebra? And then how many ways can I order my geometry books? And you would multiply all of these out, and this would be a grouping question. And grouping questions, you always figure out how many groups first, and then you figure out the permutation of each group on its own. So we got 5 people. Amy, Bill, Jill, Lee, and Tom, and they're sitting on a park bench. How many ways can they be seated? Since it's springtime, Jill and Bill wish to sit together. So it's a grouping question because we have to group Jill and Bill together. So first of all, Jill and Bill are together, and there's still Amy, Lee, and Tom. So the first question, how many groups in total do we have? We have 4. This is one group, and these singles are separate little groups. Sometimes people think of this as Jill and Bill have to be together. They're like glued together. You glue them together, and they're like one person. And so it's like arranging 4 people on the bench instead of arranging 5 people on the bench because they're glued together. Well, how many ways could you do that? 4 factorial. You can either think of them as 4 single people. There's the Amy, the Lee, the Tom, and the Jill Bill as the 4th person because they're stuck together. Then you look within each group. How many ways can the people be arranged within the group? Well, the Jill and the Bill, that's 2 factorial because they could sit holding left and right hand or sit holding right and left hand. So you have to multiply by 2 factorial. But for the other groups, since they're individuals, you don't have to write anything because there's no ways that you could just rearrange Amy. Okay? So in total, there's going to be 48 ways. Now things start to get a little contagious here, and all of a sudden now Lee and Amy also have to sit together on this. So now there's Jill and Bill that have to sit together, Lee and Amy have to sit together, and then Tom. Poor Tom. Tom gets his revenge in part C. Find out. Okay. So now how many groups do we have? 3. Or if you think of them glued together, we have like 3 single people. So 3 factorial is our groups. And then you can multiply by 2 factorial because Jill and Bill can be either way. And another 2 factorial for Lee and Amy to give us a total of 24 ways. So our numbers aren't even that high, but our counting is getting more complicated. There's sometimes you can count to like 3 million really quickly, and it's an easy counting question. And now we're getting to complicated counting questions where the answer is like 24. Okay? Now, here's Tom's revenge. Something happened, and Jill and Bill must not sit together now. Okay? But we're going to still... Okay, and we're not worried about... The only restriction in Part C, we're not continuing for Part B. Lee and Amy could sit together, they could not, but we're just trying to count all the ways that Jill and Bill must not sit together. And I mentioned this a little bit earlier in the lesson that this could be something called the not strategy, where it's too hard to count things separately. It's too hard to just create 5 spaces and saying, well, I have 5 choices here, but I don't know how many choices I have next because I might have picked Jill or I might have picked Bill. So instead, we count all the ways that they could be on the bench, which is 5 spaces, no restrictions whatsoever. Does that make sense? That would be 120. And then we figure out the bad ones. And the bad ones are where they are sitting together. We already counted that in Part A. There were 48 ways where Jill and Bill sat together. So if there were 120 in total, and 48 of those were where they were sitting together, if we subtract those away, what's left, the 72, is how many ways they're not sitting together. I mean, this is a somewhat unrealistic problem because if something like this happens, do they still go and sit all 5 of them on the park bench? No. Somebody probably be like, I'm not going to sit on that park bench anymore. If there's, but in case that does happen, this is how you could figure it out. Another strategy we haven't run into yet is permutations with cases. Sometimes it's impossible to count everything all at once. In those times, you break things up into smaller cases, count them up separately, and then once you take all of your different cases, you add them up to get your total. So here's an example. How many numbers of, at most, 3 different digits? So can you see that this could include 3-digit numbers, 2-digit numbers, and single-digit numbers? And we can't count those together because they're different cases. So what we do in these questions is we set up our cases. Case 1, we'll do the 3-digit numbers. Case 2, hey, wow. Case 2 will be our 2-digit numbers, and case 3 will be our 1-digit number. Anytime you're asked to do a cases question, you have to explain your cases. And it can be as simple of an explanation as that. You don't have to write a paragraph, an essay, or anything like that. But you just have to have some sort of indication of what you're doing as your case. For a 3-digit case, I'd have 3 decisions to make. How many choices do I have for my first digit? 10, 8, 4? Is there any restrictions? Right, so if there's a restriction, we also have to indicate with a little explanation what our restriction is. It can't start with a 0, otherwise it would be a 2-digit number. And so there would be 9 choices here. And then, does it say you can use repetition? Okay, so in this one, and you'll see this sometimes in your homework as well, where it's a little bit unclear. On your final exam, it will be very clear. Sometimes when they say using the digits, they're saying you have the digits 0 through 9. You don't have an unlimited amount of them. You have each one once. But this would be something where if you could use repetition, it would be 9 and then 10 and then 10, right? But we're going to use this on my quizzes and stuff. I might add here repetition not allowed to make sure that it's really clear. And sometimes they'll give you a list of digits. If it goes using the digits and they list them, then they're not allowing you to repeat those. So then it would be 9, 9, and then 8. 2 digits, are there any restrictions on the 2-digit numbers? Same as before, you can't start with a 0, so it'll be 9 and 9. And the 1-digit one? Ooh, it's where we have a debate. Is 0 a 1-digit number? No? Yeah, so that's what I mean. We could get into a debate. So, 0 is, but is 0 a number? Is 0 a 1-digit number or not? Okay. It's open to debate. I think I could argue that 0 is a digit and put 10 here. If you wanted to put under there that 0 was not a digit, it's not a number. Mm-hmm. Yeah, the 9, 9, because once you're not using the 0, so there's 10 different numbers that could go in there, right? But you didn't use 0, so you're only using 1 through 9. Now, one of those numbers gets used up. And now for your second choice, you have 8 of those numbers left, but now you could put 0 back in. That's why it's 9 again. And then we'd add all of these up, because each case is separate, so we wouldn't want to count them all. We'd add them up and get your total. So cases comes up with restrictions if you have 2 restrictions and the restrictions overlap each other. Okay? So here we're only using the numbers 1, 2, 3, 4, and 5. We want a 3-digit number greater than 300 and even, using only those digits. So again, this gets a little complicated as far as imagining it. Can you give me an example? Sure. 452. 452 is a 3-digit number greater than 300 and even, using only the numbers 1, 2, 3, 4, and 5. I've got 1. How many are there in total? That's what we're going to try and figure out. Now, if you try to do this all at once, and this is often the way you find out you have to use cases, you would draw, oh, I've got to make 3 decisions. What are my restrictions? Oh, this one has to be 3, 4, or 5. And this one has to be even, so my choices are 2, and those are my choices. Those are my restrictions. I have 2, so which restriction should I deal with first? Well, if you decided to use this restriction first, how many choices are there? 3. How many choices are there for this one? 1 or 2? 1, 2? Well, there's 2 if I pick the 3 or the 5, but there's 1 if I pick the 4, but I don't know which one I picked. You see where there's a problem? Because when I say 3 choices here, it means I could have picked the 3, I could have picked the 4, or I could have picked the 5. If I pick the 4, there's only 1 choice at the end. But if I pick the 3 or the 5, there's 2 choices at the end. So I have a problem because I don't know what number I can put in my second restriction, because there's an overlap of our restrictions. So the way that we do this is we set up our cases. How could I set up my cases so my restrictions don't overlap? So, okay, so if I do last digit a 2, and then this one last digit a 4, that would still count all the even ones. Now when I do my spaces, if I make this a 2, there's only 1 choice there, right? How many choices do I have for the first digit? Still 3, 4, or 5. There would be 3 choices there. How many choices for the middle? If you're not allowed to repeat. We had 5 numbers to start with. How many numbers have we used up? We've used up 1 here and 1 here, leaving only 3 left. So there are 9 numbers that end with a 2. 3 spaces for the last digit being a 4. This one's a 4. Only 1 choice there. How many choices do you have for your first digit then? Only 2, because now it can only be the 3 or the 5 because you've used up the 4. How many are left for the middle? 3. 2 times 3 is 6. And we get a total of 15 different numbers. This isn't the only way you could break up your cases. It's a nice way because it looks at the problem is with the 4. So you need to break up the cases so you once count that 4 and we don't count that 4. You could have also figured this out. Case 1, you decide to start with a 4. How many options are there then for the last number? If it has to be even, how many options do I have? 2. And 3 left. There's only 3 ways that start with a 4 that end with a 2. If I started with a 4, this is often what you have to do in cases you have to ask yourself, what haven't I counted? I haven't counted what kind of numbers? My case 2, I haven't counted starting with a 3 or 5. 2 there. How many choices are there for my last number if I start with a 3 or 5? 2, because it could be 2 or a 4. Still 3 left in the middle. Gives me 12. What's 3 plus 12? I still get 15 as my answer. I just thought of it in a different way. Some people break up that first digit into 3 cases. Start with a 3, case 1. Start with a 4, case 2. Start with a 5, case 3. Whichever way you decide to break up your cases, the basic idea is when you have an overlap of one of your restrictions, you're going to have to use cases. And you're going to have to break up one of your restrictions into 2 things or more things to break up that restriction. So at first we looked at the last restriction and broke it up with end with a 2, end with a 4. And that allowed us to count things separately and add them up. We could have looked at the first restriction and broken that up. Start with a 3 or 5, or start with your 4. And that would have worked as well. Now, we're going to use the numbers 1, 2, 3, 4, 5, and we need to make it greater than 232. Now, these greater than questions come up a fair bit. And the way that I like to do these greater than ones with numbers, it no longer has to be even. So the problem lies with our first digit. How many choices do we have for our first digit? If we just tried to do this all at once, what could our first digit be? A 3. Okay, that's one possibility. Let's list them all. 4, 5, and 2. Okay? So it appears that we have 4 choices here. The problem happens with the next space. How many choices do you have next? Well, if you chose the 4, it could be anything that's left, right? But if you chose the 2, you have a problem. Because then it couldn't be anything that's left. Because you couldn't put 2 and then 1. But you could go 4 and then 1. So what I like to do with any ones that have greater than is case 1, try to guarantee. So I'm going to start with, if I start with a 3, a 4, or a 5, that's going to guarantee that I'm going to be greater. So if I do my 3 spaces for my 3 decisions, and I start with a 3, 4, or 5, there's 3 choices there. Now it doesn't matter because I'm guaranteed that my number will be larger. So how many numbers do I have left? Because I've used up 1, 4. And then how many numbers do I have left? 3, because I've used up 2 of the numbers for 36 ways. Case 2, what haven't I counted? I haven't counted starting with a 2, comma. Then my next number, if I want to guarantee that it's bigger, I'm going to go 4 or 5, because that's going to guarantee that it's bigger. So if I start with a 2, and then 4 or a 5. I have one choice here, two choices here, and then my third decision, there's no restrictions on it. How many numbers are left? There's still 3 numbers left. Because I have 2 choices doesn't mean I use both the numbers. I used one number here, one of those 2 numbers here. So if I use the 4, the 5 can still get put into that last space for 6. Are there any cases I haven't counted? Right. I haven't counted case 3. Start with 2, then a 3. So if I start with a 2 and then a 3, one choice there, one choice there. If it needs to be bigger than 232, how many choices do I have here on the last one?
2.
Which ones? 4 and 5. So it's good to write out the numbers, because you're going to be tempted to want to write 3 there, because you think, oh, what numbers are bigger than 2? 3, 4, and 5. But can you see you've already used up the 3? So the only possibilities left are the 4 and a 5 for 2 choices. Once you've counted up all of your cases, add your cases together, and there's 42 in total. 44? Thank you for adding better than me. 44 in total. Excellent.